Hey, hello, ib2 higher level students on next amazing video lesson. Amazing because still doing photoelectric effect. Okay, I hope you are prepared to the lesson. You have pen, pencil, ruler, your powerful calculator, a notebook, and of course Tsoko's book. Yes? Okay, so let's do revision, a short revision of our last lesson. We are talking about photoelectric effect. So this photoelectric effect is emission of photons from the surface of the metal when it is illuminated by light which has enough of frequency, enough of energy. So you know that photoelectric effects occurs only when light has a certain frequency which is bigger than a certain frequency called threshold frequency or critical frequency, and energy which is carried by light is given by equation Planck's constant times frequency. This energy is energy of, or it is a portion of energy or quant of energy. So energy which is carried by one light particle called photon. When this photon hits the surface of metal, then it can emit an electron from the surface of metal. Of course, if this energy is high enough, because each electron needs a certain amount of energy called work function to be emitted. Okay, so if photon has more energy than energy needed to emit an electron, then electron is emitted from the surface of metal, and rest is of course a kinetic energy of emitted electron. So again, left hand is energy of photon, right is energy needed to remove electron, and the rest is kinetic energy of removed electron. So basically this equation is simple law of conservation of energy. Okay, energy which is delivered by the light is used to emit photon from the surface, and rest is kinetic energy of this removed electron. So again, energy carried by light is equal to the energy needed to remove electron from the surface, and the rest is kinetic energy of this removed electron. And of course, this kinetic energy can be or half of mv squared when v is a speed of emitted electron, or this is charge of electron times a voltage, because Einstein did something like a stopping voltage experiment. Yes, he used this metal surface which was illuminated by light. Electrons were emitted from the left plate traveling to the right plate, and he connected this to the variable power supply which delivers voltage in opposite direction that potential difference produced by removed electrons. He connected also ammeter and a voltmeter. Okay, and the idea of this was to check a voltage by using voltmeter for which no current flows in the circuit. What does it mean? If no current flows in the circuit, it means that power supply delivers exactly the same voltage as voltage which is created by this photo effect. Basically, in this case, this voltage needed to stop the current is equal this kinetic energy of electrons is equal to the charge of one electron times voltage needed to stop this current. So basically, if this voltage, this one read by voltmeter, is known, we can calculate kinetic energy of electrons. If kinetic energy of electrons is given, we can check this equation, because usually frequency of light is known, so we can calculate our work function, or if work function is known, we can calculate frequency. Remember about units, usually here the energy is given in electron volts. If you want to calculate frequency or wavelength of light, you have to convert it into joules, of course. Is it clear? So as the next part of our revision is this 1 electron volt is 1.6 times 10 to the power of minus 19 of joules. Okay, So what is important here? Important is that photoelectric effect occurs only when light has a frequency bigger than critical frequency, which is strongly related with type of the surface. Yes? So if energy of light is bigger than work function, so energy needed to remove electrons, then electrons are emitted. Okay? Second, light delivers energy in parts, in portions, in quants. In each photon has energy equal h times f. And third, one photon can remove only one electron, so effect occurs instantaneously. There is no something like accumulation of energy by one electron. Electron doesn't wait for, I don't know, hundreds of photons to collect high enough energy to be emitted. No, it happens instantaneously, which means that one electron can absorb only one photon, or other words, one photon can hit only one electron. Is it clear? Okay, fourth one. Intensity of light means number of photons. So if more intense light is, then more photons in the stream and more electrons can be removed, but each of removed electrons has exactly the same kinetic energy given by this equation. Yeah? Okay, so here we have some details about photoelectric effect in the form of revision. So next, if you don't have this, I don't know why, you should have this in your notebooks. If you don't have this, please copy this. It's very, very important topic. Okay, and next slide, I'm going to focus on graphs. We did one graph last lesson, how kinetic energy of removed electrons depends on the frequency of light. Okay, so due to this equation, HF is equal to work function plus kinetic energy, we can plot a straight line graph, because kinetic energy, due to this equation, is HF minus work function. So if kinetic energy is on y-axis and F is on x-axis, then Planck's constant is given by a gradient, and phi minus phi, this work function, is given by y-intercept. So the graph is a straight line which crosses y-axis at negative parts, so this negative y-intercept is equal to minus work function, and x-intercept, so this is this critical or threshold frequency. I use term threshold, Tsokos uses critical, so let's use critical frequency, so minimum frequency needed to remove electron from the metal surface. Okay, and we did this last time also, so this is also a kind of revision. And so what happens if we have another surface? Okay, so let's imagine that now another surface is illuminated by a light surface with bigger work function. If we have a bigger work function, then more energy is needed, so bigger critical frequency. So for another work function, we have a line which is parallel to this original blue one, which crosses the axis, okay, in different part, so we have different work function, and different work function means that another critical frequency is needed. So let's name this phi2 and fc2. Of course, lines must be parallel, because again, what is represented by gradient? Gradient is Planck's constant, which is a constant which must be the same. Okay, so remember, if another surface is illuminated, another surface means another amount of energy needed to remove electrons. So if another surface is illuminated by light, we have a graph which is parallel to this original, which crosses y-axis in different place, because there is another work function, another energy which is needed to remove electrons from the surface. Of course, if another amount of energy is needed to remove electrons from the surface, there must be another critical frequency, and the graphs must be parallel, because again, gradient represents Planck's constant. Okay, So if gradient is a constant, then it must be the same angle between the line representing graph and the x-axis. So lines are parallel. Is it clear? Okay, so now let's focus on another graph, how the current, photocurrent in the circuit with stopping potential depends on the, let's say, work function, or how the current depends on the, let's say, frequency of light. Yeah. So topic is the same, photoelectric effect. If you want to write new topic, it should be photoelectric effect with number of 2. Okay, so let's create a graph. Maybe first let's create again a circuit. So again, we have a plate, a surface, photosurface, which is illuminated by light. Okay, and let's imagine that light has enough of frequency to emit electrons. So electrons are emitted from the surface and travel from one plate, let's say left one, towards another plate, let's say right one. Okay, so of course all is kept in the vacuum. Electrons should not interfere with another particle. There is a kind of opening through which light can enter this. Okay, and of course this is connected to external power supply, which is variable, to very sensitive ammeter, and we have to know voltage, measure voltage delivered to the system, so we need voltmeter. Okay, so again, what is the idea here? Electrons are removed because light delivers energy. Okay, so one photon can remove one electron. If energy is high enough, then electron is removed, and the rest is kinetic energy of removed electron, which is stopped by this stopping potential. If ammeter reaches 0, then this equation works. So amount of volts needed to stop electron in this circuit is linked with the frequency of light by this equation. Okay, so now let's focus on the graph, how, let's say, intensity of current, this is not intensity of light, this is intensity of current, so I'm going to use this, depends on the voltage of this power supply. Okay, so you can open your SOCOS on page number 485. Oh, sorry, SOCOS 485. Okay, and in SOCOS on page number 485 you have very interesting graph. I'm talking about these two graphs, graph number 12.3 and the graph number 12.4. Okay, so let's focus on graph 12.3. So let's look. Let's imagine that this surface is illuminated by light, okay, and electrons are emitted. Yeah, so photoelectric effect occurs. So if we have a voltage bigger than this certain, called stopping voltage, like here, okay, then electrons, if electrons are emitted from the surface, then we can stop it by supplying a certain voltage to the circuit. Is it clear? But if this voltage is less, then of course photocurrent in the circuit is bigger than current which is created by this power supply, so ammeter can read some current. So practically we have a voltage above which current starts to flow. Okay, so graph looks like this. So if no external voltage is delivered to the circuit by power supply, this is 0, okay, then current of course flows. Yeah, there must be a certain voltage delivered to the surface to stop these electrons, to stop electrons in the circuit, and this voltage is called stopping voltage. Okay? So now let's imagine that we have the first graph. I'm talking about first graph. Let's imagine that intensity of light is less. Okay? What does it mean? So this is high intensity of light. Okay, so now let's imagine that we have a light which is less intense. For less intense light, we have exactly the same equation. Okay? Intensity of light doesn't influence the condition for photoelectric effect and doesn't influence the kinetic energy of emitted electrons. So stopping voltage must be the same. For less intense light, we have the same stopping voltage, which means that current starts to flow in this circuit exactly above this voltage. But if light is less intense, then less electrons are emitted. Okay, if less electrons are emitted, we have less charge in the circuit in unit time. The same voltage and less charge means that less current in the circuit. So for less intense light, we have a line which starts at the same point because stopping voltage is the same, but we have less current in the circuit because less electrons are emitted. Again, intensity of light means number of photons, means number of electrons which are emitted. Is that clear? Okay, and let's focus on another graph. The same quantities. Intensity of current in this circuit versus voltage, this external voltage delivered by power supply. And again, let's imagine that we have a violet light. Okay, and let's imagine that photoelectric effect occurs for violet light, so we have a certain stopping voltage. So if voltage is not delivered or is less, then current starts to flow in the circuit. So if there is no external voltage, we have a certain current in the circuit. This is exactly the same situation as in graph above. Okay, so now let's imagine that the same surface is illuminated by light of less frequency. So violet means high frequency. And let's imagine that the same surface is illuminated by green light. Green will be less frequency. Okay, and let's imagine that photoelectric effect occurs. It means that this frequency of green light is high enough to emit electrons in the circuit, which means that H times F for green light is still bigger than work function for this given material. Is that clear? So what happens if less intense light is delivered to the circuit? If less intense light is delivered, if less intense light is used, then of course, let's look, stopping voltage is different. If we have smaller frequency and the same work function, then stopping voltage must be less. Is that clear? So to stop electrons for less frequent light, we have less stopping voltage. Okay, so this stopping voltage for green light is different than stopping voltage for violet light, because light, green light, has less energy, has less frequency. Okay, so let's say green of lower frequency. Okay, so you see these two effects in first graph. We have effect of intensity of light and the current in the circuit. So if intensity is different, then we have different current but the same stopping voltage. And in second graph, we have an influence of frequency of light and the current in the circuit. So if we have light which has lower frequency, which means less energy, then stopping voltage must be also lower. Is that clear? Okay, details, maybe not details, the same graphs you have in SOCOS on page number 485. Okay, please copy this. You can write point graphs or photoelectric effect graphs. Please copy this, it's also important. And let's do some exercises, okay? So let's calculate something. Okay, now open your SOCOS on page number somewhere here. No, a lot. Oh, and page number 502. Okay, page number 502. Okay, and let's focus on the first exercise today. Maybe. Oh, this is classical. Maybe exercise number 2 or 3 or 5. Okay, so maybe exercise number 2. Okay, first exercise number 2. Okay, so what evidence is there for the existence of photons? So try to answer this question. This is theoretical one. I give you answer in a few minutes, so maybe let's read to A and to B. What evidence is there for the existence of photons? And B, a photosurface has a critical frequency of 2.25 times 10 to the power of 14 Hz. Radiation of frequency for 3.87 times 10 to the power of 14 Hz falls on this surface. Deduce the voltage required to stop electrons from being emitted. Okay, so please stop video for a moment. Let's say for first 2 minutes, for the second 5 minutes. So we have 7 together 8 minutes to solve this problem or try to solve this problem. So now please stop video for 8 minutes. When you will be ready, please turn it on. Start. Okay, so 8 minutes later, yeah, after 8 minutes. Okay, so what with A? What evidence is there for the existence of photons? A photoelectric effect, yes? Photoelectric effect is one which can be explained only by using the model of light as a stream of photons, okay? Photoelectric effect cannot be explained by wave nature of light. It can be explained only by photons, so photoelectric effect. And B. So let's write data. We have critical frequency. So again, this is minimum frequency for which photoelectric effect occurs as 2.25 times 10 to the power of 14 of Hertz. And we have a radiation of frequency 3.87 times 10 to the power of 14 of Hertz falls on this surface, and deduce the voltage needed to stop electrons from being emitted. So the question is about stopping voltage. Okay, by using this you can calculate work function. Again, critical frequency is minimum frequency needed to emit electrons from the photosurface. So critical frequency is the frequency of light for which light has energy the same as work function, so minimum energy needed to emit electrons from the surface. So you have to multiply Planck's constant, minus 34 times this frequency, which is given to the 25 times 10 to the power 14 of Hertz, which is, still I don't have my calculator, 6.63 times to the 25 is 14.9 times 10 to the power of minus 20, or 1.49 times 10 to the power of minus 19 of joules. This energy here is given in joules because we've multiplied Planck's constant given in standard unit times frequency given in hertz. Okay, and now we can use equation H times F is equal V plus we are looking stopping voltage, so you can write this in the form of Q times Vs. Left hand 6.63 times 10 to the power of minus 34 times frequency of light, which is given here, 3.87 times 10 to the power of 14 of Hertz, is equal to work function we've calculated here, so 1.49 times 10 to the power of minus 19 plus charge of electron, which is 1.6 times 10 to the power of minus 19 times stopping voltage. So you have equation with one unknown. Use your calculator and calculate Vs, and then Vs will be given, of course, in volts. Okay? So I hope this exercise was not difficult. Remember here what the critical frequency is. Critical frequency is the minimum frequency of light for which photoelectric effect starts to occur. Or other words, it is the frequency of light for which energy of light is equal work function. So energy needed to remove electrons from photosurface. Okay? So copy this if you don't have, and next slide, next exercise. So example 2. Last example today. Let's take exercise number 3 from your Tsokos. Okay, again, this is page number 502, exercise 3. Okay, read the exercise with me. A light of given wavelength falls on photosurface and causes the emission of electrons of maximum kinetic energy of 2.1 electron volts at a rate of 10 to the power of 15 per second. The light is emitted by 60 watts light bulb. Explain how light causes the emission of electrons. Calculate the electric current that leaves the photosurface. Determine the work function of the surface. Estimate the maximum kinetic energy of electrons when the intensity of light becomes 120 watts. And estimate the current from the photosurface when the intensity is 120 watts. Okay, not easy exercise, kind of challenging. Okay, so please copy this to your notebook and try to solve these 5 points. You have, let's say, 20 minutes. Okay, so please stop video for 20 minutes. Try to do this the best as you can. It's challenging but not too difficult. It's of course solvable. So after 20 minutes, when you will be ready, please turn video on and check and compare with my solution. Is it clear? So start 20 minutes. Okay, so after 20 minutes. So let's check your answer A. Explain how light causes the emission of electrons. Okay, first of all, you have to write that light is a stream of photons. Each photon has energy H times F. Okay, then you have to write that one photon can remove one electron. Okay, next you have to write that if energy of light is bigger than work function, then electrons are removed and rest of the energy is delivered to the electron in the form of kinetic energy. Just these 3 points, yes? So light is a photon. Okay, one photon can remove one electron. When energy of light is bigger than work function, then electrons are removed from the surface, and the rest of this energy is delivered in the form of kinetic energy to the electrons. I hope you had this. Okay, B. Calculate the electric current that leaves the photosurface. Okay, so let's look. What is the electric current? Electric current, okay, is charge which flows in unit time. Okay, so if you calculate charge which flows in 1 second, then you have an electric current. So what do we have here? The important data is, let me read the text, electrons of maximum kinetic energy at rate of 10 to the power of 15 per second. Okay, so here is written that the light causes the emission of electrons of maximum kinetic energy, which is given at rate of 10 to the power of 15 per second. So let's look. Charge of electrons is number of electrons times charge of one electron. So charge of one electron times number of electrons emitted is total charge emitted in 1 second, because this number 10 to the power of 15 is given per second. So it is 1.6 times 10 to the power of minus 19, this is charge of one electron, times 10 to the power of 15, because this is number of electrons removed per 1 second, which is 1.6 times 10 to the power of minus 19 plus 15 is minus 4 of coulombs. So what is a current? Current is 1.6 times 10 to the power of minus 4 coulombs emitted in 1 second, which gives 1.6 times 10 to the power of minus 4 amperes. So this is the answer for B point. 1.6 times 10 to the power of minus 4 amperes is the current which flows in the circuit, because current is charge over time, and we know that charge is 10 to the power of 15 times 1.6 times 10 to the power of minus 19 per 1 second. Okay, C. Determine the work function of the surface. Okay, so C is classical. So what is a work function? Work function is given in this equation. Yes, so energy of photon is equal work function plus kinetic energy of removed electron. So to find work function, you have to know what is the frequency of light and kinetic energy of removed electrons. So one by one. Frequency of light. Frequency is not given directly, but we have a wavelength. Okay? So wavelength of light is 5.4, and we know that light moves with speed of c. So this is speed of light divided by wavelength, which is 3 times 10 to the power of 8 divided by 5.4 times 10 to the power of 7, which gives 3 over 5.4, which is 0.56, 0.556 times 10 to the power of 8 minus 7. Something is wrong, sorry. Frequency. Oh, there is a mistake in Tsakos. In my Tsakos, yes, there is a mistake, because it should be minus 7 here. Okay? Yeah, so here we have not 7 but minus 7. Okay? I write this as a comment when I link this video. So it will be to the power of 15 or 5.56 times 10 to the power of 14 of hertz. Next mistake in the Tsakos. So I hope that you remembered about this, because before I will upload this video, I will write this as a comment to the video, that in this exercise should be minus 7. Okay? Oof. So frequency is given. Now what with kinetic energy? Kinetic energy is charge times stopping voltage. No, we don't need to use charge times stopping voltage, because we know this kinetic energy of removed electrons is 2.1 electron volt. So all you have to do is to convert this into joules. So remember, 1 electron volt is 1.6 times 10 to the power of minus 19, which gives 2.1 times 1.6 equals 3.36 times 10 to the power of minus 19 of joules. And now you can use this directly. So phi is equal Planck's constant, frequency minus kinetic energy. I'm not going to calculate this, but you have to substitute 6.63 times 10 to the power of minus 34 times frequency calculated here, so 5.56 times 10 to the power of 14, minus kinetic energy calculated here in joules, so 3.36 times 10 to the power of, we have to obtain a result, of course, in joules. Is it clear? Okay, so C is solved. Now D. Estimate the maximum kinetic energy of the electrons when the intensity of the light becomes 120 watts. What does it mean? We know that now the previous intensity was 60 watts. Now we have 120 watts. So what does it mean? It means that intensity of light increases by 2. So what does it mean? We have 2 times more photons, and 2 times more photons can remove 2 times more electrons. Okay, so this is the effect of increasing the intensity of light. In 60 watts we have 2 times less, 50% of photons than in the stream which has 120 of watts. Remember, what is the energy in unit time? So in total, 120 watts light has 2 times more energy in total. Each photon has the same energy, but we have in stream of photons 2 times more photons because we have 2 times more energy. So 2 times more photons can remove 2 times more electrons, but each removed electron has the same energy because intensity doesn't influence energy of single photon, so doesn't influence energy of emitted electron. Okay, so what is the maximum kinetic energy of electrons when the intensity of light increases? Maximum kinetic energy of electrons stays the same, so it is 2.1 electron volts, or as you calculated here, 3.36 times 10 to the power of minus 19 of joules. Okay, so again, intensity of light doesn't influence energy of single photon, which means that doesn't influence kinetic energy of electron removed by this photon. It's very important. Okay, and last one, E. Estimate the current from the photosurface when the intensity is 120 watts. Okay, so if intensity is 120 watts, which means that we have 2 times more photons or 2 times more electrons, then what happens? Electrons were emitted with a rate of 10 to the power of 15 per second. So now the rate of emission of electrons is 2 times 10 to the power of 15 per 1 second. Okay? So current I equals Qt, okay, will be 2 times bigger because now we have 2 times bigger charge. So no 1.6 times 10 to the power of minus 4, but 2 times 1.6 times 10 to the power of minus 4, because in 120 watts light we have 2 times more photons, so 2 times more electrons emitted, so total charge which is emitted is 2 times bigger. So current in this case will be 2 times bigger, not 1.6 times 10 to the power of minus 4, but 3.2 times 10 to the power of minus 4 amperes. Okay, so what is the difference between D and E? In D, we have more intense light means more electrons, but each electron has the same kinetic energy, so kinetic energy of removed electrons is exactly the same. In E, 2 times more intense light means 2 times more electrons, so current in the circuit is 2 times bigger, the same stopping potential, but current must be 2 times bigger because we have 2 times more electrons in the circuit, so 2 times bigger charge, so 2 times bigger current. Oof, I like this example, a classic one. Okay, so let's open SOCOS on still we're on 502, and your homework is exercise number 4 and exercise number 5. Okay, so I will upload this lesson as assignment because your task will be to include this solution of these two exercises, okay, as assignment. So please write answers, please write solutions for these two exercises, and please add this in the form of PDF as an assignment to this lesson. Yes, so COCOS 502, exercise number 4, A and B, and exercise number 5, A and B. Okay, so I see that in the case of calculations you have here something to calculate and here something to calculate, because rest like this, three aspects of something, or like this, what happens if are theoretical questions. So this is your homework, it's obligatory. The deadline is to, let's say, Sunday, because I expect these exercises at Monday's morning, so you have deadline to Sunday. So thank you for watching. I hope it was interesting to you. I like this topic, you have to like also, because you can find a lot of exercises related with photoelectric effect in your past papers. So again, if you have any comments and suggestions, please write as a comment to the movie or in the Google Classroom. This is your homework, obligatory. I expect PDF files with solutions from all of you, okay, in the Google Classroom. Again, thank you for watching. Learn physics and stay at home. Bye.